Let me try once again. Okay, so if you have any questions, you can ask them at the end. If you are watching us in YouTube, you can type them in the chat and I will read them to André. I have a warning to make. Next week we won't have any seminars because we are attending a congress, and in the other week Carol is going to talk to us in English, so if you don't speak Portuguese, you are welcome to join us once again at the first Wednesday of December. Today's speaker is André Barato. He obtained his bachelor and master's here at University of São Paulo. He is PhD at University of Würzburg. He was a postdoc at ICTP, University of Stuttgart and Max Planck Institute, and now he is a professor at University of Houston. He works with stochastic thermodynamics, and the title of today's talk is Precise Oscillations in Stochastic Thermodynamics. Thank you, André, and you can start now.
Okay, so thank you for the invitation, and thank you for everybody for attending. Today I'm going to talk about oscillation in stochastic thermodynamics. I mean, the common thing is that I typically look at precision in its relation with dissipation, or the kinds of bounds of thermodynamics that thermodynamics can bring up in precision in when there are oscillations. And I'm going to talk about what I mean by oscillations. So in my abstract of this talk, I did say I was going to talk about time crystals, but I don't think I'll have time to talk about that. I mean, I think online talks that are really long are kind of boring. So, I'll just mention this, but I'll talk about mostly biochemical oscillations like circadian cycles, and I'll talk a little bit about also spatial oscillations like in Turing patterns, okay? And, I just mentioned my work on related to time crystals that we did recently. Okay, so, in the very beginning of this talk, I'll just make an introduction to stochastic thermodynamics. After this introduction is done, I will really talk about our results on oscillations and precision and dissipation, the relation between precision and dissipation, oscillations, stochastic thermodynamics, okay? So, let's do a little bit of an introduction to stochastic thermodynamics in case you don't know. Okay, I have a problem. Okay, it's fine. Okay, so, this picture here is supposed to represent stochastic thermodynamics. So, in the first figure, you see a train moving. That would be what I call standard thermodynamics. So, the train might be kind of a non-equilibrium system, and this might not be standard thermodynamics. But anyway, when you have thermodynamics, we have system in equilibrium. The system is typically big. There are like 10 to the power of 23 constituents. So, fluctuations are negligible. So if I look at a train, I don't see. I only see the train moving forward, right? I don't see like a Brownian motion or whatever. And the second example is a molecular molecule on a track. Like it's like the train, it moves forward on average. But if I watch a motor, it's just a single molecule. It's a large molecule, I don't know, 70 times bigger than the water molecule. And the motor is not going to just walk forward; it's going to fluctuate. So there are huge fluctuations. The motor can be out of equilibrium, and the big difference between stochastic thermodynamics and standard thermodynamics is that it can deal with systems at finite time. I mean, remember when you do your thermodynamics course, you never see time, right? You go to the whole course, unless you're a professor with linear response theory. Typically, nobody does in a standard thermodynamics course. So you don't ever see time, right? There's no time. It's just a series of equilibrium states. Things are supposed to be really, really slow, so there is no time. Fluctuations are negligible, so very large number of constituents, and you go to the equilibrium states, right? That's standard thermodynamics. Stochastic thermodynamics, we want to remove these constraints. We want to do with things like molecular motors, single molecule and colloidal particles. Those are like the experimental setups to which the theory applies. And so that's the stochastic thermodynamics. That it's an extension of thermodynamics to this non-equilibrium, finite time, and small system case, okay? Okay, so these figures are supposed to represent some of the experimental systems to which the theory applies. So the first one is this is like a heat engine. It's like a Stirling heat engine, but not really. So you just have a colloidal particle. You apply some potential, which is represented by this parabola with, I don't know, optical tweezers or whatever. And first you move the stiffness of the potential. So, you change the parabola a little bit, you make it less stiff. I guess I should say it less stiff, right? You make the parabola larger. So that you just change, the potential is 1/2 k squared. So you just increase k. Then you change the temperature, right? And then you move from the second part to the third part. And then you change from the third part to the fourth part by changing the stiffness back. And then you change the temperature again. Okay, that's a cyclic engine. Again, the difference from this engine to a typical Stirling engine that we would see in a thermodynamics book is that this is a small system, just a single colloidal particle. It's finite time, right? I can do this engine as fast as I want or as slow as I want. And so this is like a heat engine, but again, finite time in a small system. The second example is what people call a catenan. So these are two interlocked rings. Now, this is a whole field, this is called a molecular pump. So people try to just do some artificial molecule that does something, right? The goal of the field like this is to create artificial molecules that would do something like a molecular motor does. But in any case, from the perspective of stochastic thermodynamics, that's just a kind of an engine, or that's just a small molecule that does something. Okay, what it does here is that this small ring should move kind of in the clockwise direction with respect to the big ring. Okay, that's called a catenan. There are lots of interesting experiments with that. The third experimental system is just a molecular motor. That's F1 ATPase. In this case, it just rotates. It burns ATP, use chemical energy to rotate. And even if you attach a big probe to it, like a big particle to it, it will rotate and carry the particle. And you do chemical work, and part of this chemical work is going to be transformed into mechanical work to move the particle. And the third one is a quantum dot. A quantum dot is like a dot which can either be empty or occupied by an electron. And again, these are all examples to which the theory of stochastic thermodynamics apply, or at least may apply depending on the regime. Like the quantum dot must be in a certain regime of weak coupling, whatever. But these are all experimental setups to which the kind of theoretical results I'm going to talk about, and then to which the results of stochastic thermodynamics apply. Okay, so these are the experimental systems we have in mind when I talk about this theory. Okay, so, and if you have saw a talk of mine, I always do the introduction, so it's a little bit repetitive, I'm sorry, but I always try to at least do a little bit of introduction to stochastic thermodynamics. Okay, so before I move on, let's just say what we mean by stochastic thermodynamics. So, one of the simplest systems you could imagine in stochastic thermodynamics is like a colloidal particle. This would be a overdamped case. So we just have a Langevin equation. X is the position of the particle. V is some external potential that I can apply using optical tweezers. This particle is in some liquid. Maybe this particle has some electric charge, and I apply some electric field, and then there is some force, which is this green force. And if I write down the Langevin equation for this particle, mu would be the mobility. I have the derivative with respect to space of this external potential, and I also have this force, and then I have some noise eta, right? And so this would be a Langevin equation for this particle. And there is a name we will find in stochastic thermodynamics, which is this external protocol. In this case, if this particle is just if this potential is just a parabola, changing the protocol would be I can either change the center of the parabola or the stiffness of the parabola, and that would be changing an external protocol. So if I change this with time, that would be changing an external protocol. Okay. Now, what I would like to do is to define heat and work. Okay. So first, work. If I just, for example, one contribution to work is just FDX, right? That's what we learn in classical mechanics. That's the typical definition of work. There is another definition that if you do, I don't know, thermodynamics course, a standard one, you might not see this kind of work there, which is, for example, if I move the parabola from the red position to the green position, now my particle was sitting at the center of the red parabola, but it's not sitting at the center of the red parabola anymore. So clearly the energy of the particle has increased now. Now the particle is sitting some higher energy at this green parabola. So if I move the center of the parabola, I change the energy of the particle, right? And the work I do is just V of x lambda star. So lambda star is the new protocol minus V of x lambda, okay? So and if I do some infinitesimal change in dW, that would just be dV d lambda multiplied by d lambda, okay? So there are these two contributions to work. One is just FDX. The other is this small, maybe less usual contribution, which is dV d lambda d lambda. That's what's called Jasinski work, and it's what shows up in Jasinski equality typically. And so, I mean, of course, this dW is something I can do for every stochastic trajectory. So, there is a major difference between standard thermodynamics and stochastic thermodynamics. This major difference, this is one of them, is that if I do, I mean, in thermodynamics, we don't think about single stochastic trajectories, right? We think about entropy as an average quantity already. So we think about entropy already associated to some sort of an ensemble trait. So, entropy, energy, these are all average quantities when we do a typical thermodynamics course. Here, I want to define work, heat, entropy, all these things for every single stochastic trajectory, okay? So if I just move the particle a little bit, I should be able to associate work, heat, and energy to every single stochastic trajectory, okay? And work is easy, right? If I just move the particle, dW would be just the dV, dW plus FTX, okay? That's just work. And energy, in this case, I mean, there is no other internal energy, just the potential energy that I'm applying to particle. And if I want to define heat, I just use the first law. I assume the first law is true for every single stochastic trajectory, which should, of course, be true, right? I mean, and, the definition of heat is that heat is whatever is left, right? So first law must be true, and heat is just whatever is left in the first law, okay? That's the best definition of heat I'm aware of. Heat should be defined as whatever is left. It's not very elegant, but I think it's the best definition of heat. Okay, so that's the heat, and if I just think about the whole trajectory x of t, I can just do an integral of these things. So if I want to calculate w, I do an integral over the w, and again, this is a stochastic integral, might be complicated to do. You have to introduce some sort of path integral formulas to do it. But in any case, all I'm trying to convince you here is that the huge difference between stochastic thermodynamics, or at least a huge difference, is that we want to define heat, work, and entropy for every single stochastic trajectory. Okay, so that's the definition of work, and heat was defined as whatever was left. Okay. Okay, so I should say before I move forward that this is not something very surprising. I mean, although the first person, the first time people really defined, for example, the first time people took a Lagrange equation and really defined heat and work for every single stochastic trajectory, as far as I know, is the work of Sekimoto, and this is, I think, 98, 96, and it's mid-90s. But, this is not something really new in the sense that, Maxwell in 1877 already knew that, in a sense. I mean, if we were to, tell Maxwell that, we are up to defining heat and work for every single stochastic trajectory, I think he would be very bored. Because he knew that already. I mean, here he's talking about Maxwell's demon, but which is another story. But in any case, when he's talking about violation of second law here, he's really imagined. I mean, he can only write a sentence like this: "Hence, the second law of thermodynamics continually being violated." And when he's talking about it, he's imagined like some molecule that has moved, and he can only think about this kind of violation in this sentence if he's thinking about entropy as defined for every single stochastic trajectory. Okay? He's just imagined a trajectory where, for example, a fast molecule went to the hot side or something like that by mistake. Okay, that's what he's thinking about here. And so this is not, although this is formally very different from thermodynamics. This is not really a new idea in a sense. I think Maxwell already knew about that. Okay, he already knew that you could think about these quantities at the level of single stochastic trajectories. Okay, so if I have this definition of heat, and when I think about this colloidal particle, it's in contact with a heat bath at temperature T. Okay, a very important thing about stochastic thermodynamics, even though we do think about systems that are out of equilibrium, it is important that a constraint of the theory is that we deal with reservoirs that are in equilibrium. Okay, so we do have a big reservoir at a constant temperature T, and it is in equilibrium, right? And if I have a reservoir in equilibrium, the entropy change of the reservoir, which is the entropy change of the external medium, is just the heat divided by the temperature. That's the definition of entropy. Again, that's a stochastic entropy because that was a stochastic heat, so it's defined for every single stochastic trajectory. If I want to define the stochastic entropy change of the system associated with the trajectory x of t, again, so just to be clear, the trajectory of x of t is this trajectory that I have drawn here. Okay, for every single trajectory, I can define a functional, which is the work, the heat, and now the entropy. So if I just define minus ln of p plus ln of p minus ln of p final plus ln of p initial, as the system entropy change, and I take the average over all trajectories. That's what the brackets mean here. I would just get channel entropy. So, the entropy of the system, or the non-equilibrium entropy of the system, is just the channel entropy. That's how we define entropy. And, the total entropy is just the entropy change of the medium plus entropy change of the system. Now, very important formula in stochastic thermodynamics is this one. So if I think about a trajectory and I think about a reversal trajectories would be a trajectory that starts in the final point of the forward trajectory and finish in the initial point of the forward trajectory. So that's a reversal trajectory. I should also apply the reversal protocol. So, if I have moved my potential from left to right in the forward trajectory, in the reverse trajectory, I move it from right to left, okay, whatever. So I just apply the reverse protocol. And I'm not going to show this formula. I mean, if you want to do it for Lagrange equations, you have to use a little bit of path integral formalism, but that's a fairly simple formula to show. It's just that that's actually the definition of entropy also. But the total entropy is just a ln of the ratio of the forward trajectory divided by the probability or the weight. I mean, this probability, but if I want to be rigorous in math, it would be the weight of the trajectory divided by the weight of the backward trajectory. Okay, that's a very explicit relation between entropy and irreversibility. Okay, and again, this is true for every single stochastic trajectory. And from this relation, it's almost a tautology to derive the fluctuation theorem. And that's the fluctuation theorem. Okay, if I look at the probability distribution of entropy, it should fulfill the relation, which is known as Crookes relation. Now, the tilde over the trajectory means that is the probability distribution for the reversal protocol. But in any case, you can look at the right hand side equation, which is e to the power of minus delta S total is equal to 1. And this equation is a little bit more general than the Jasinski relation, which e to the power of minus W over T is equal to e to the power of minus delta F over T. Okay, so I told you that Maxwell would not be very surprised if we had told him that, we are doing entropy for every single stochastic trajectory, but this here, with this relation here, for sure, he would be very surprised. Okay, that's quite something. I mean, there is absolutely nothing like that in standard thermodynamics. So if you think about the first average is the average of e to the power of minus W divided by T is equal to the power of minus delta F divided by T. So delta F is the free energy difference. That's an equilibrium quantity, and I can relate it to something which is a completely non-equilibrium quantity. So it's, this e to the power of minus W divided by temperature is, and KB here is 1, okay? This is the work done during a completely non-equilibrium process, okay? So if you imagine this colloidal particle experiment, I can move this trap as fast as I want. So I can change this, I can do whatever I want with my harmonic potential. It cannot even be non-harmonic. I can change it as fast as I want. It doesn't really matter. I calculate the work during this completely out of equilibrium process, and I can relate an equilibrium property to the work done during a non-equilibrium process. Okay, again, there is absolutely nothing like that in thermodynamics. Okay? This is really a big revolution in thermodynamics and statistical mechanics. Okay, so if you do the whole course on thermodynamics, and I'm going to teach it next semester, statistical mechanics, you never see time. Okay, there is no time. And here I'm doing finite time. I can change the trap as fast as I want. It doesn't really matter. The relation is still true. Okay. These are two experimental demonstrations of the fluctuation theorem. On the left is just a colloidal particle on the ring, and on the right, and these are non-Gaussian probability distributions. I just want to tell that, and this thing has been verified in many different experiments. So, one big thing of stochastic thermodynamics, I think, one thing is the formalism, right? We define these things, but those are just definitions. I can define entropy and heat at every single stochastic trajectories. That's how I define things. But the fluctuation theorem is really the big result that really started stochastic thermodynamics. Okay, because the thing here is that fluctuations out of equilibrium, they cannot be any. Okay, there are constraints on them, and I think in stochastic thermodynamics, the really interesting thing, or the main question in stochastic thermodynamics, is try to find universal relations about fluctuations in out of equilibrium systems. Okay, and after the fluctuation theorem, which was done, fluctuation theorem was discovered in the mid-90s by Galavotti and Cohen, and by Jasinski independently. These were different versions of the fluctuation theorem also. But then in 2015, myself and Udo Seifert, we discovered something else called the thermodynamic constraint relation, which I think is also a very universal relation about fluctuations out of equilibrium. I'm just going to briefly explain what it is. So if you imagine like a single enzyme in a solution, so the enzyme is just constantly taking substrate and producing the product. Now you should imagine that the concentrations of substrate and product are constant. There are just too many of them as compared to whatever the enzyme is doing. So that's typically a non-equilibrium steady state. So the enzyme is constantly burning. Substrate could be ATP and product could be ADP plus PI. So it's constantly burning ATP. And that's an experiment you can do in principle. And, let's say you want to look at the output of this chemical reaction, which is the number of products that are produced, okay? So X is this random variable. X is a random variable. So if I run this chemical reaction for 10 minutes, and 10 minutes is much larger than my relaxation time. So I'm just in a steady state during this whole 10 minutes. So if I just run this chemical reaction for 10 minutes, and I can look at the total number of product that was produced by the enzyme, if I do an experiment like that, whenever the enzymes produce a product, I would just see a blink in my experiment. And I can just count this. It's easy. I don't know if it's easy, but it's possible. Never did the experiment. But in any case, I could do this experiment. And so I can just count this number X, which is the number of produced products. So if I run this for 10 minutes, X can be 100. It could be 2, it could be 1,000. In each realization, it's going to be a different number. It could be even negative, right? I could go to a case where actually the enzyme has consumed the product. Okay, so it could be -2 also. So, X is just a random variable, and I can define an uncertainty of X. So, I could imagine that there is a chemical reaction going on in my body, and I want this chemical reaction, the product of this chemical reaction to be precise because it triggers something else in my body. And the question is, what is the cost of the precision of this chemical reaction, okay? And what we found is that the cost, C, which is, in this case, the cost is just the total free energy cost. So, of burning ATP. So, if I'm just constantly burning the substrate S, and I want to relate the precision with the energetic cost. Please note that if I am in equilibrium, so if I'm in equilibrium in this case, X, the average X is going to be 0, okay? In equilibrium, it means the probability of consuming the substrate or consuming the product is the same. And I just go from left to right in this enzymatic scheme, right? I would just go from here to there. It would be as likely as going from right to left. Let me ask you something. Can you see the cursor, my mouse cursor, when I move it or not? Can anybody ask? All right. So if I would go from here to there, if I was in equilibrium, the chance equilibrium would mean that the chemical, yes. You don't see it anymore. All right. Okay. So, if the chemical potential of S and P are the same, both have the same chemical potential, that would be equilibrium. I would just go from here to there, as likely as I would go from there to here, or from left to right, as likely from right to left. And so, that would be I'm in equilibrium. The average X would be 0, and my uncertainty would be infinite. Okay. So if you want to have some sort of precision, you must dissipate energy. And what we have found is that the total cost multiplied by the epsilon square must be larger than 2 kBT. Okay, so if I want to get 1% precision, I have to pay 20,000 kBT. Again, this is very general. It's true for any stochastic process. And it's true for any current in any stochastic process. So whatever I do, if I do a quantum dot, a molecular motor, and I look at the thermodynamic flux, and I look at the precision of the flux, the precision of the thermodynamic flux is bounded by the total energetic cost of the process, okay? That's the thermodynamic constraint relation. It is a very universal relation, maybe not as universal as the fluctuation theorem. I think the fluctuation theorem is valid for, I think the conditions for the fluctuation theorem to be true are a little bit less restrictive. But in any case, this has been a big advancement of stochastic thermodynamics after the fluctuation theorem, has been this thermodynamic constraint relation. And so, once we have discovered that, we were very interested in the relation between precision and dissipation. And I think the first system we have in mind were like biochemical oscillations. So, there are these biochemical oscillations that happen in our body, like the circadian clocks. And, you probably want these things to be precise. And we wanted to understand the relation between precision and dissipation there. So that's the first thing I'm going to talk about, is the relation between thermodynamics and coherent oscillations in biochemical oscillations. Then I'm going to talk about very recent work, which is the relation between precision and dissipation in spatial oscillations. And number 3 is just really going to do a little bit of advertising of what we have done with subharmonic oscillation and stochastic systems. But this will be just one slide, and I'll just say what we have done. Okay, so let's start with biochemical oscillations. So, when I talk about biochemical oscillations, I mean, there's just a bunch of molecules interacting. Okay, you just put a bunch of molecules in water or whatever liquid, you let them interact, and this is a model. This is called the activator inhibitor model, and there is some enzyme M. It goes through a cycle, and there is an X and an R. There is an X. I mean, this blue means that MP generates X, MP generates R, then X repress R. So when you have this kind of feedback loop, you kind of see oscillations. So if I look at the concentration of X and I do a trajectory in this model, I see oscillations, as you can see in the figure, as a function of time. And this is a stochastic model, so these oscillations are not totally precise. So let's say you have a circadian clock, okay? And so you want the period of oscillation to have 24 hours. But if you have stochasticity, maybe sometimes it's 24 hours and sometimes it is 25 hours because it's a stochastic system, okay? And the question I want to ask is, how precise are those oscillations? And as far as we could think of, I think the best quantity to characterize this precision is the number of coherent oscillations, okay? What's the number of coherent oscillations? So, instead of looking at a single trajectory X, I can calculate the correlation function, the time 2-point correlation function in time C, right? Which is just the average of all the oscillations, okay? And if I calculate this correlation function, what will happen is that this correlation function is gonna oscillate with the same period. If it was a circadian cycle, it would be a 24-hour period. And this oscillation will also decay exponentially, okay? And the number of coherent oscillations is the decay time divided by the period. Okay? If I have a very large number of coherent oscillations, it means that I have a good biochemical oscillator, okay? And again, I mean, the idea here is that, suppose imagine a stochastic person, okay? Imagine you take a person, but not like a 10 to the power of 23 constituents person, like a stochastic person, something that's fluctuating, and you put this person in a black room, right? There is no stimulus from the outside anymore. There is no external signal of light day and night. And I want to ask, for how long will this, this number of coherent oscillations tell me for how long will the internal clock of this person work, okay? So that's what the number of coherent oscillations tells you. It tells you how precise the internal clock of this person would be. But again, I'm not imagining a person. I'm imagining a bunch of chemical things interacting. And I imagine something that's stochastic, so there is some sort of 100 or 1,000 of molecules interacting with each other. And I mean, this is something that can be done experimentally, just to be clear. There is, I guess, the best experiment you can do is with a molecule called Chi-C, so K-A-I-C. So that's a molecule that is found in cyanobacteria. And, this molecule is responsible for the circadian clock of cyanobacteria. And if you just take this molecule and you put it together with 2 other molecules, one is called Chi-A and Chi-B, but the most important one is Chi-C. I mean, they're all important for the function of the oscillation, but the thing that really oscillates is the phosphorylation level of Chi-C. So if you put all these molecules together in a solution with ATP, and the phosphorylation of level of the Chi-C are going to oscillate with a 24-hour period, okay? So, this experiment you can do. You can put a bunch of molecules and you can look at the conformational change of the molecule, and you can look at some property. In the case of Chi-C, it's the phosphorylation level of the molecules. Again, it's something you can measure experimentally, and you just do an experiment with a bunch of molecules, and this bunch of molecules is really a circadian clock. And the question I'm asking here is, how good is your circadian clock? And by how good, I mean for how long it will keep oscillating in a coherent fashion before it dies out, okay? So the number of coherent oscillations tells you, because, if you wait too long, the clock is going to dephase. By that, I mean, if I have a circadian clock, and if I wait from a time that is much, much longer than my decay time, so if I look at the number of oscillations that is much larger than the number of coherent oscillations, so, if my number of coherent oscillations is 30, but I'm looking at oscillation number 3000, if I look at 2 different systems, one will be in day 3000, the other is going to be in late 3200. Okay, they're going to be completely dephased from each other. Okay, they're going to be counting different number of days. All right, so that's the number of coherent oscillations. And I mean, the question we wanted to ask is, what's the bound of the number of coherent oscillations? Okay, I mean, so if I think about this activator inhibitor model, that's just a bunch of chemical reactions, whatever they are. So that's the paper where they introduced this model. It's just a bunch of chemical reactions. And the question is, if you give me a bunch of chemical reactions, I mean, if you fully specify this set of biochemical reactions, then you also tell me what are the thermodynamic forces at play. So, in case of and I mean, the thermodynamics force at play is something you can know. Okay, you just have to know the temperature of the system. You would also have to know, if the system is burning ATP, you would have to know what's the free energy of ATP hydrolysis, which in physiological conditions it should be 20 kBT. So these are all things you can know in an experiment. So if you just tell me what's the set of chemical reactions, and you tell me what's the thermodynamic force, I want to be able to tell you what's the maximum number of coherent oscillations that system can do, okay? And that's the bound we found in the number of coherent oscillations. Okay, so, that would be the master equation for the activator inhibitor model. I don't want you to understand this equation. I'm just saying that, if you give me a set of chemical reactions, whatever these chemical reactions, as complicated as they might be, doesn't really matter. I can just write down a master equation for it, okay? And again, a hard thing to ask this question is to really formalize the problem. I mean, it took us a long time to really formalize the problem. Again, the answer we wanted to ask is, what's the bound on number of coherent oscillations? Okay, how well can a biochemical system oscillate? And I mean, I'm assuming that a biochemical system is well described by stochastic processes. Okay, that's it. That's what I wanna. That's the message I wanna convey here. So if you give me a set of chemical reactions, I assume that stochastic Markov description is a good description, which is a pretty safe assumption, I guess, with biochemical systems. And if you give me a set of biochemical reactions, I can write down the master equation for it. How long it may be, doesn't really matter. And so, because of that, now we can formulate the problem. And the way to formulate the problem is the following: you give me a master equation, and I mean that's the equation that will describe this set of chemical reactions. Now, that's the formal solution of the Maxwell equation. L is the stochastic matrix, or the adjoint of the Markov generator if you are a more mathematical person. And I can go ahead and calculate the eigenvalues of this matrix. The first eigenvalue is going to be, and by the first I mean the largest one, or the one that is not negative, is going to be the zero eigenvalue. That's one is associated with the stationary solution. And in stochastic thermodynamics, all systems are ergodic, so there is always a stationary solution. So if you have a biochemical system, you always are going to have a stationary solution. Then I'm looking at the second eigenvalue, and the second eigenvalue, or the first one that's not zero, that's one that has the less negative real part one. It has some real part and some imaginary part. And the number of coherent oscillations R that I use here is just the imaginary part of this eigenvalue divided by the real part. That should be equal to 2p tau over t. Tau is the decay time, and t is the period of oscillation, okay? So, the way you formalize this question is, I mean, you just look at the first excited eigenvalue, and you look at the ratio of the imaginary part and the real part, okay? I want to find a bound on this thing, the imaginary part of the first excited eigenvalue divided by the real part, okay? That pretty much up to a factor of 2 pi is going to give me the number of coherent oscillations of my system, okay? So, we have took this problem, the general problem of oscillator, a biochemical oscillator, and we have formalized the problem, and that's the bound we want to find. The bound on the first, on the ratio of the imaginary and real parts of the first excited eigenvalue. Okay, so the way we found this bound, I mean, this is still not proven. It's a conjecture, but I'm pretty sure it's true. But I really don't know how to prove it. It's not so easy. So the way we did it, first we start doing it for a unicyclic network. So imagine you just have an enzyme. The enzyme has different conformational chains, right? So the enzyme goes from E1 to E2 to E3 until En, and then it goes back to E1. So that's just a unicyclic network of states, so just a cycle. And this is the simplest kind of thing I can do. That would be the stochastic matrix for this network. And the thermodynamic affinity, which is the driving force, that's just the chemical potential difference that's driving your cycle. So, in order to be out of equilibrium, this A here has to be non-zero. If A is zero, you're in equilibrium. So, I define this thermodynamic affinity. And so the bound I want to find is if I fix the affinity in the number of states. So if I know what's the network topology. So if I know the set of chemical reactions, I know the network topology. And I fix the thermodynamic force. Again, the thermodynamic force is something that I should know. So if my system is driven by ATP, I know that my thermodynamic force is 20, or 20 multiplied by whatever is the number of ATP that I burn in a single cycle. What we found is that in this case, the number of coherent oscillations is bounded by this formula here. Okay, so this is a nice formula because if you give me a system, you tell me the network of states, which is represented by n here, the number of states, and you tell me what is the affinity or the thermodynamic force, I can find a bounded number of coherent oscillations, okay, which is given by this formula. Again, this is information you should know about the system. I guess the set of chemical reactions might be harder to know, but the thermodynamic force is easy to know. And if you send n to infinity, this is a divided by 2 pi, okay? So the number of coherent oscillations is just bounded by the thermodynamic affinity divided by 2 pi. This is what we found for a unicyclic world network. I think not even this one we can prove. Again, the evidence for the unicyclic world is really strong. I'm sure it's true, but I think rigorous proof we don't even have for this one in unicyclic network. And it turns out that this is also true for multicyclic networks, okay? It's true for whatever network we look at. For the multicyclic network, you just have to search for your best cycle. So the best cycle, so each cycle is a function. This function is a function of a and n. N is the number of states in the cycle. A would be the affinity of the cycle. You just look for all cycles in your network, and the best one gives you the largest bound. And the number of coherent oscillations is just going to be bound by your best cycle. Okay. Now I should say this bound was known in math without the A. Okay. So if you send the affinity to infinity, this tangent hyperbolic become 1, and that R is bound by cotangent of pi over n is known in math. It was a problem posed by Kolmogorov in a conference, and some master students, Russian master students, managed to find this bound. But it was only known with the n, without the A. Okay, but the A is really the important thing from the perspective of stochastic thermodynamics. The really important bound is the one that involves A. Okay, so in the end, what this bound is telling you is that the number of coherent oscillations is bounded by the thermodynamic force. Again, this is not thermodynamic cost. Okay, it doesn't involve entropy production. This A is not something that I have to calculate. It's something that I know already. Okay, so if you give me a certain biochemical system, if you give me a system with 100 Kc, each Kc burns, I think each Kc can burn 6 ATP. So if I have 100 Kc, it would be 100 multiplied by 6 multiplied by 20, which is the free energy of 1 ATP hydrolysis. And then I have to divide by this 2 pi, which will give me something like 300. So, with a bound like this, you give me a system of molecules with Chi-C, which is the experiment I can do. I can tell you that system is going to have a maximum number of coherent oscillations of 300, which is like a year. So the system can go for a year if it has 100 Chi-C, okay? So, again, if you just tell me a set of biochemical reactions, I can tell you for how long that thing can oscillate. Just to reiterate, that's the bound in general. That's still a conjecture. We can't prove it. And it's not so easy to prove it, I guess. The conjecture is that the ratio of the imaginary and real part of the eigenvalues is given by that. Now, again, these eigenvalues are going to control typically your correlation function. So, that will be a bound on the number of coherent oscillations, okay? And again, the A star here is just the affinity of the best cycle. The best cycle, so again, cotangent of pi over n, tangent hyperbolic of A divided by 2n is a function of A and n. The best cycle is the one that has the largest function, f of A and n, okay? Okay, so that's the bound on the number of coherent oscillations. I think it's a very important result. I think it has been kind of underappreciated, to be honest. It's almost as important as the thermodynamic constraint relation, in my view, but it's different from the thermodynamic constraint relation. I don't know what's the relation between both of them. I don't think that is, if there is one, it's something very hidden, because, I don't think there is much of a relation between the kind of point that appears in the thermodynamic constraint relation, which is the uncertainty, and this relation of xi over xr, okay? This is like calculating the first excited state of a matrix in quantum mechanics, and the uncertainty relation you can calculate by doing perturbation theory, right? You can do perturbation theory in quantum mechanics to calculate the first excited state, right? So, I don't think there is a relation. I don't know if there is a relation between both. If there is one, it should be kind of non-trivial. And again, this is very different from the thermodynamic uncertainty relation. Okay? The thermodynamic uncertainty relation involves the cost. It involves the entropy production. The entropy production is a quantity that depends on your dynamics. Okay, this A here doesn't depend on the dynamics. This is really a thermodynamic bound. Okay, the input. You ask me what's the maximum number of coherent oscillations, and the bound I'm giving you is something that does not depend on any dynamics whatsoever. It just depends on the thermodynamic force driving your system. Okay, So that was the bound on the number of coherent oscillations. Now, what we have done more recently, I mean, this is a case of a temporal oscillation, and we were interested also in spatial oscillations, okay? And for spatial oscillations, the simplest model you can think of is probably this 1D oscillator model. So, you know, you have these chemical species A and X and Y. A, S, and P are all chemical species that have fixed concentration, so there are chemiostats fixing them. So you have this set of chemical reactions, and but I mean, now I have dimensionality. Okay, before I have kind of a mean field model, it's just a bunch of molecules in water or whatever. But now I have cells I, and the molecules have chemical reactions within each cell, but they can also diffuse between different cells. So they can go from I to J, where J would be I plus 1 or I minus 1 in a one-dimensional model. Okay, so now I have a model of dimensionality. I have chemical reactions, and I mean, that's the simplest model probably you can think about of this kind of thing. And I mean, this model forms a Turing pattern. So, you know, the idea of a Turing pattern is the following. So you have a totally homogeneous model here. So, you know, all cells are the same. They all have chemical reactions on them. And Turing introduced the idea that if I have a homogeneous system with chemical reactions and diffusion, and if there is a time scale difference between these diffusions, Turing introduced the idea by doing a deterministic model with rate equations that a pattern, a spontaneous pattern, can be formed. Okay, again, that's a quite revolutionary idea. It's a beautiful paper, and you know that has been a lot on spontaneous pattern formation and Turing patterns. I don't really want to discuss this literature. I just want to say that if you do a model like this, I mean, a spontaneous pattern is going to be formed. Okay, you are going to look in space at the concentration of X. There's going to be some sort of oscillations, of spatial oscillations, and I want to analyze the precision of spatial oscillations. So before I was thinking about temporal oscillations, now I want to think about spatial oscillations. Okay, and I mean, I should advance. So what we found before is something very universal. It's a full bound on the number of coherent oscillations. I mean, I'm not going to be able to find something like this here because, you know, that's much more complicated. It's a one-dimensional model. We are going to have to resort to simulations for this case. And, you know, what we did here is really a case study. It's not, there is no universal bound coming out of it, but we had a nice, interesting result with this case study. So the case study, we analyze this model and we analyze the precision, the relation between the precision of the spatial oscillations and dissipation with this 1D oscillator. Okay. Okay, so that's the model, the 1D oscillator. That's the phenomenology of the model. Okay, so delta mu is the chemical potential difference. So let me go up. So the chemical potential difference is the chemical potential of S. S could be ATP again. P could be ADP plus PI. So S is the substrate, P is the product. So the chemical potential of S minus the chemical potential of P, that's the delta mu. Okay, that's the driving force that drives my system of equilibrium. So if delta mu is 0, these chemical reactions would be in equilibrium. If delta mu is large, I'm very far from equilibrium, and so on and so forth. Okay, and you know this chemical potential difference is related to this A1, A2, B1, B2, C1, C2, which are my transition rates. Alpha and beta are the transition rates for the diffusion. And you know, if I choose this transition, I fix all these transition rates and I just vary one of them, and I vary in such a way that I'm just changing my chemical potential. What I see is that if the chemical potential is small, I don't see any oscillations in my system. So n is the number of X molecules and m is the number of Y molecules. Okay. So you know, if the chemical potential is small, I don't see oscillations. And if the chemical potential is larger than some critical value of the chemical potential, which was around about 1.1, I think, 11.1, I see oscillations. So you know, if the chemical potential is large enough, I see oscillations. If the chemical potential is not large enough, I don't see any oscillation. Okay. So if you know the amount of energy dissipation or the chemical potential is big enough, there is a Turing pattern. There is a pattern, and I is space. Okay, that's space. So this is a simulation of a system of size 200, and you know I can see that the amplitude of the oscillations is larger for the X molecule than for Y molecules. But clearly on the right hand side I have oscillations, and on the left hand side I just have fluctuations. There are no oscillations there. Okay, these are just fluctuations, just a constant fluctuating. Okay. Now the question I want to ask is, you know, this is a stochastic Turing pattern. Okay, this is a stochastic model for a Turing pattern. The question I want to ask is, what's the relation between the precision of the Turing pattern and the amount of energy dissipation? Now, I'm not going to discuss the energy dissipation because it's kind of trivial here. What happens if you calculate the entropy production is that entropy production, or the amount of heat that's being dissipated. Here, heat is being dissipated because you are constantly consuming the substrate and producing the product. Okay, So if it was ATP, you're just burning ATP all the time. Okay, that's the heat that's being dissipated here, or the free energy that's being consumed. Okay? It's probably a better name. Free energy consumption is a better name than heat. But you are constantly consuming free energy, and you can calculate the entropy production or the ratio of free energy dissipation. It's just an increasing function of delta mu. Okay, the larger delta mu, the more energy I dissipate. Okay, that's the energy dissipation. But let's look at the precision of the pattern. So how do I characterize the precision of the pattern? So the first thing we did to characterize this precision was to look at the distance between two different peaks. Okay, so if I have a deterministic model, this distance between the two peaks would be all uniform, and they would be the same, and there will be no fluctuation in this number. Now, if I have a precise pattern, I should have a small uncertainty in this variable. Okay, so I define this variable. I mean, W1 would be the difference between two peaks, and W2 difference between the other peaks, and W3, and so on and so forth. And then I look at my whole pattern, and I make an average over my pattern. I also make an average over different. I mean, this average here is an average over different realizations. Okay, and I make an average over several different realizations, and that's the result I get. Now, as I told you, the energy dissipation is an increasing function of delta mu. Okay, so what the result tells us is that the precision of the pattern is best at some intermediate middle level of delta mu. Okay, and again, these are just different times. Okay, this is for how long I run my simulations. As you can see, it never gets stationary. I mean, the blue is close to the red one, and I mean, you cannot really do longer than that. But this pattern seems to be kind of meta-stable things. But in any case, the result here is that the optimal precision happens at some intermediate level of delta mu. So if I dissipate more energy, I mean, if I increase delta mu beyond 11.3, I dissipate more energy and I get less precise. Okay, so there is an optimal amount of energy dissipation if I want to have a precise pattern. Okay. This is a little bit non-intuitive. I mean, it can happen, but I think that's a general result, okay? And I think it's a general result because of the following. So if you watch a movie of this thing, so, if I watch a movie of these patterns, what I see is that these patterns, if I was to run a movie with time, I would see all these peaks fluctuating, okay? And as I increase energy dissipation, or as I increase delta mu, they're fluctuating less and less, okay? So when I say fluctuations here, I mean fluctuations by you watch a movie of these patterns, you look at the peaks and they move, they fluctuate left and right, okay? So as I increase energy dissipation, these fluctuations actually get smaller and smaller. But even if the fluctuations get smaller, it does not mean that the precision of the pattern is better. What happens is if you have no fluctuations, if fluctuations are really, really small, and if you enter some sort of meta-stable state where the peaks are not at the right position, they are not at the right distance from each other, it is going to be very hard to leave that position. I mean, you enter a meta-stable state, and because fluctuations are small, it's very hard to leave that position. Okay, so you just get stuck into a meta-stable state. So, I think the general lesson to learn here is not so much that there is this intermediate value for which, I mean, this is an interesting result that there is an intermediate value. So if I increase energy dissipation, my precision gets worse. But what I find even more interesting is the fact that fluctuations have also they also have a beneficial effect for the precision of the pattern. So if I don't fluctuate, and I enter some meta-stable state where the distance between two peaks is not what it should be, I will stay stuck there for a very long time because I don't have fluctuations to correct me. So fluctuations have the bad effect, which is fluctuations make the pattern bad because it fluctuates, but they also have a good effect, which is correcting the pattern. Okay. Now this random variable W is very hard to define with an equation. So I would not know how to write it down with an equation. I mean, we can do a simulation, look at the peaks and measure it, but it's not very formal in the sense that I don't know how to define it with an equation. In any case, we have looked at something else. We have looked at the spatial correlation function, okay? And if you look at the spatial correlation function, and having a larger number of oscillations of spatial, this is spatial oscillations, okay? Those are not temporal oscillations. If having a large number of spatial oscillations means I have a more precise pattern, then clearly that the same result is true, right? I have some intermediate value of delta mu. So if I increase dissipation beyond that value, my precision gets worse. And if I'm below that value, is also worse. So there is an optimal value, and increasing dissipation beyond the optimal value will just make your precision worse. So we are typically trained to think that more dissipation will let you better precision, but it's not true in this case. And again, I think that's kind of general because I think typically as you increase dissipation, you will make your fluctuations larger, but larger fluctuations does not always mean that it's good, because again, if you enter a metastable state and you need your fluctuations to correct you, without fluctuations, you don't manage to correct to the right state, okay, to the right distance between the peaks. So that's like kind of the general lesson I think we can learn from this model. And again, I think this thing of having an intermediate value of the dissipation and of increasing dissipation beyond the optimal value will lead to worse dissipation, worse precision. I think that's kind of general for this Turing pattern, these spontaneous patterns, okay? Yeah, let me move forward. So I'm done. I told you I was not going to talk about subharmonic oscillators in stochastic system. I mean, I don't want to go talk too much about that. We did a couple of papers about that. I think this is a very interesting subject. Now, what I mean by subharmonic is the following. So there are two ways of driving a system out of equilibrium. I talked about systems that are like just non-equilibrium steady states, right? They just have some chemical potential difference that drives a constant flux. But when I think about like heat engines, like I showed in the first slide, I can drive a system in equilibrium with an external protocol that's periodic. So I can have a Hamiltonian and change this Hamiltonian periodically with time. And then I can have some sort of, I drive a system of equilibrium with this external periodic drive. And one thing I've asked in this paper, in this first paper that I'm called Limit on Subharmonic Oscillations in Stochastic Systems, is that, I mean, I look at subharmonic oscillations. Okay, so let's say I have the period of variation of my Hamiltonian is 1 minute, and I want to look at oscillations of 24 hours. So I look at oscillations. I want to look at a system that has oscillations with a period larger than the period of the drive. Okay, and again, I think there's a very open problem in stochastic thermodynamics, because I think the first paper that's ever looked at that is our paper. Even in math, people don't really do that. They don't look at you have to do Floquet theory to do that, and you have to look at these Floquet exponents. And I think people have really not done that for stochastic processes anyway. But I mean, one result we have found in this paper is that if I have a subharmonic oscillation, what we saw with the NAS case, with the steady state case, is that if I have a system with 3 states, my maximum number of oscillations was cotangent of pi over n, right? It's cotangent of pi over 3. That's the maximum number of coherent oscillations I can have. Now, if I look at subharmonic oscillations in stochastic system in a periodically driven system, then there are no limits there. Okay, even if I have a 3-state system, the number of coherent subharmonic oscillations can go to infinite. Okay, there is no limit to how long you can go. So the subharmonic oscillations in periodically driven systems are not bounded by the ones that the oscillations that we see in non-equilibrium steady states. Okay, and they I mean they can also I mean this is an interesting idea, because if you think about these biochemical oscillators, if you think about biochemical oscillations, there are all kinds of oscillations going on. There are oscillations that have order of magnitude minutes. Some oscillations have order of magnitude days, which are the circadian ones. Then there are some order of oscillations that might have a month, or it depends on the biological oscillation. And if you think that one might be a signal that influences the other, I mean, what we found in one is that if you have some signal that influences your Hamiltonian with one period of 1 minute, and you are looking at a 24-hour oscillation, the signal of period with 1 minute can drastically change the relation between the number of coherent oscillations and thermodynamics. Okay, that's I think the main found of one. Now on 2, using the model from 1, we managed to build a stochastic thermodynamics model for a time crystal. So a time crystal seems to be kind of a big thing in the last couple of years. It was the idea that you could have oscillation in an equilibrium quantum system. It turns out it's not true. You can't have it, but you can have something that people call discrete time crystals, which are subharmonic oscillations in Hamiltonians that are periodically driven. And what we have done in this paper, which is almost accepted, is that you can have subharmonic. I mean, you can build up a model using the things we found in one. We build up a model. This is a 2-dimensional model that has like a number of coherent oscillations that diverge in the thermodynamic limit, and you know, that's what people call a time crystal. And we could build a model for the time crystal that's thermodynamic consistent. By that means a model for a time crystal for which you can calculate thermodynamic cost and so on and so forth. Okay. Okay, so arrive at conclusion. The first thing I told you is that if you tell me what are your biochemical reactions, I can tell you for how long can you oscillate, or what's the number of coherent oscillations of can have, or I can tell you after which time are your oscillations become bad. I mean, you know, if I compare two different realizations, when are they going to dephase? I can tell you that. You just have to tell me what is your set of biochemical reactions and what's your thermodynamic force. I told you that, you know, increasing dissipation can make a Turing pattern less precise. So, and I think that's kind of general. Although we just did a single model, I would expect that to be general. I think, you know, this idea that that fluctuations can also have a beneficial effect in the precision of the Turing pattern, I think that's kind of general. I told you a little bit about subharmonic oscillation stochastic systems, but, you know, I didn't have time to go through that. And, you know, I just want to say what I think the question of stochastic thermodynamics, or, you know, I think, you know, if you want to be really famous in stochastic thermodynamics, you should try to find something like this. And the question is, what are the universal laws that rule fluctuations of small unequilibrium systems, right? I mean, the fluctuation theorem is one, the thermodynamic uncertainty relation is another one. I mean, I think this bound on the number of coherent oscillations is another one also. You know, it tells you, I mean, it's a pretty general bound on the correlation functions of a stochastic system. You know, it has an application for circadian clocks and so on and so forth. So, you know, thank you for your time, and I'm happy to get some questions.
Thank you, André. So, does anyone have any
question? I have one question, but
Go ahead, Fury.
André, first of all, many thanks for your seminar. Thank you very much. I liked it very much. Just let me ask you something. In your first application about the reaction, the bound, does your bound you proved, you showed us, does it hold valid for any kind of reaction, for example, a catalytic reaction, or not? It's only for the shape reaction you showed us.
No, the conjecture is true for any stochastic process. So whatever stochastic process you have, you look at the correlation function. I mean, the stochastic process should be within the realms of stochastic thermodynamics, but, you know, it should be ergodic and so on and so forth. But that's a given. I mean, it's going to be, if it's a biochemical system, it's going to be. But, you know, if I give a stochastic process that potentially has a stochastic thermodynamics, so, you know, pretty much almost any stochastic process. And if I look at the first eigenvalue of the stochastic matrix, the ratio of the imaginary part and the real part is going to be bounded by this thing. And I mean, okay, I can't prove that, but I'm pretty confident it is true. Okay. As confident as I was about the set relation before we proved it, or before someone else.
Thank you. Thank you.
Any more questions?
Yes, I have a few questions. So, thanks, André, for a very interesting talk. Certainly moving forward in this area. My questions are about the Turing pattern.
Yeah.
I have three questions that I think are short questions, and I'll ask them all together, and then you can reply. First, do you think it's interesting to look in this context at a noisy Swift-Hohenberg equation? The second is, in the Turing pattern that you studied, could it be that there are subsequent bifurcations that occur as you increase the dissipation rates? And third, what about dimensionality effects? Is it possible that above d equals 2, the pattern stabilizes because of something like Mermin-Wagner? I know Mermin-Wagner doesn't apply, strictly speaking, on equilibrium, but there still might be dimensionality effects. Those are my questions.
Yeah, so I mean, we still don't know. I mean, yeah, I don't really know what would happen for large dimensionality, static dimensionality. I think a lot of things can happen. There could be a lot of effects at play. I mean, it's really open question, but yeah, what you say, it might be correct. It's kind of non-vague, yeah. But I mean, the answer would be that we don't really know what's going to happen. I mean, there is pretty much nothing done on this field. I mean, I think we just did the first thesis study, and you know, there could be bifurcations at higher delta mu. I don't know, but yeah, I think at least for the model, we look at if you keep increasing delta mu, your precision is just going to saturate. I mean, it's going to reach a certain level, and you know, I mean, whatever is the figure you have done. Yeah. At least if you think about precision, and again, I think this quantity here is not so good in the sense that it's not very well mathematically defined, but you know, this correlation function is very well defined, and it really tells you what's the precision. So you know, if you keep increasing delta mu beyond 12, I think at some point the correlation function is going to be completely saturated and look the same, and it will have almost no oscillations. So you know, if you just keep increasing delta mu, at least from the perspective of the precision of the pattern, your pattern is not going to be very precise, I guess. But the reason for that, I don't know. It might relate to what you're saying about bifurcations, I don't know. And yeah, I think that's what I can say for now. But what I would say about this is that really our work is really the first study. I mean, there have been works on Turing patterns and stochastic thermodynamics, but they have not looked at the relation between precision and dissipation. And I think our work was the first one. We just did the simplest possible model, and we looked at what was the simplest possible thing we could conclude about within the simplest possible model. I think the simplest possible thing we concluded that there should be some optimal level of dissipation. I mean, there should be some optimal level of dissipation. If you go beyond that, you probably get your precision worse. But yeah, I think these are all interesting questions. And another interesting question would be, you know, this is the case of a model which only has spatial oscillations. There are chemical waves, right? There are models where you have spatial and temporal oscillations at the same time, which are called chemical waves sometimes. You know, with I mean, it might be interesting to look what happens when you have spatial waves, spatial and temporal waves. It's interesting to look at what happens to other models, as you mentioned. I don't know the exact equation you mentioned, so I don't know this equation very well. But it would also be interesting to, and dimensionality also, you know, because there are many things that happen in Turing parts with dimensionality. It's a very large field, and there are many things there. So, you know, I think this is still a very open thing, the relation between dissipation and precision in Turing patterns. Though, you know, I think one of the authors, you know, was in the seminar I saw Gian Maria Falasco there, and I think he has a paper on the relation between Turing patterns and stochastic dynamics. That was more like setting up the formalism for the case of the deterministic rate equations. This is a little bit different. But you know, I think this is very open thing, and all these things you mentioned, the relation with dimensionality, the relation between chemical waves, and many other things, and the relation between precision and dissipation. And if I can mention, I think something that would be very nice would be, I don't know if this exists or it's possible, but you know, finding some sort of general relation between spatial precision and dissipation, like the thermodynamic concept relation. So the thermodynamic concept relation does not really involve spatial precision, that's the precision of thermodynamic flux. But you know, finding a general relation between spatial precision and energy dissipation, like the thermodynamic concept relation, would be huge. That would be very interesting. I hope I have answered your question.
Thanks. Well, yes, I think you did. And possible ideas for future study. Thanks.
I should mention, you know, again, Gian Maria Falasco, I think you are here, right? I don't know if you are still here, but I think you were in the beginning. So he does have a paper, nice paper on Turing patterns and stochastic dynamics. But again, this is a formalism for Turing patterns, and it's more for deterministic Turing patterns.
Yes, I'm here.
Thank you for the talk, it was very nice, and it's totally true what you are saying, that this is the thing, this precision in space was, you were the first to look at, to be interested in this kind of of topic, and what we did was just to set up a theory for the deterministic case.
Okay, thank you.
Any more questions? So maybe I think that's it. So thank you once again, André, and thank you everyone for joining this seminar. And just a reminder that in the next week we won't have any seminar because there is the Congress of the Brazilian Physical Society. But in the other week the first week of December we will be back. So thank you and bye.
André, thank you very much for your nice talk.
All right, thank you.
And,